So chapter 9 is about momentum, and then section 1 is about impulse. So when we have a collision, there is a short duration interaction between two objects. So that's basically what a collision entails. So we have examples: the tennis racket hitting a ball, the foot hitting the soccer ball, like we have in the pictures here. Also, when a car hits another car, when something is dropped on the floor, all kinds of things. Those collisions, uh, if you were to map out kind of how the force is actually um, being spread out over time, you would see that there is a short amount of time where the impact, we'll say, is interacting between the two objects where the collision is actually occurring. So they're not instantaneous, is the point. So if we look at the soccer ball being kicked, this is a perfect example of what is actually going on. So the contact begins here. We notice that the foot here is straight and the ball is still round. Okay. And now as we kick the ball, we are compressing the ball. We're also kind of compressing our foot. The foot is flexing. So we notice this arch in the foot, and also we have this big compression going on in the ball. The ball is no longer round there. And that's true of any ball. A baseball, basketball, if we were to throw a basketball at the rim, um, a football when we kick the football, a golf ball, especially if you watch a slow motion video of a golf ball being hit off the tee or something, the golf ball is being compressed.
Why would you kick a football or a golf?
Not kicking a golf ball, we're hitting the golf ball off the tee with a club. So now the ball is in motion. Okay, so the ball is moving. And then the contact is ending, so the foot is no longer flexing. It's back to mostly straight. And the ball is no longer compressed. It's back to mostly round. And the ball has now received all of that impulse from the compression. It is now flying through the air, or it's about to fly through the air. So the duration of the collision that's going on depends on the materials that are involved. This ball here with the kick, the soccer ball kick, is more flexible, so the duration would have lasted longer. The harder the object, the shorter the contact time. So the idea here is the soccer ball was way more flexible depending on how inflated it was. We would have had a longer duration of impact, so the contact time would have been longer. The collision between the two pool balls, if you've ever played pool, you know those are extremely hard. So the duration of the impact between two pool balls lasts less than 1 millisecond, while a collision between the foot and the soccer ball might last 20 milliseconds, so 20 times longer.
It's still really short.
But it's still very short. That's right. But still 20 times longer between two pool balls versus the soccer ball and the foot. So great compression implies greater restoring force. So the restoring force, just like the spring that we were dealing with back when we were talking about springs. So we could potentially think of this as like a spring situation. Okay, so moving on. What we need to look at is when we have the contact force beginning, so when the kick is occurring, back if we still think about the kick and the soccer ball. So the contact begins, and then as the contact begins, the soccer ball is being compressed. So we're going to have a point of maximum compression up at the top of this peak. And then the ball starts to move faster and faster. It's being accelerating away from the foot. And then the contact ends. So now over here, the contact is ending. So that means we had a duration delta t, how long the compression of the ball was going on for. And that's going to be our duration of impact then. Okay. Now, notice that we have this big curve here. Kind of looks like the bell-shaped curve if you've studied.
Probability?
Yeah, if you studied probability, right? So that would be more like statistics, though. So the curve here has an area underneath it, and we can talk about that, and we'll do that later. So looking at this kick again, when the contact begins, the ball is only slightly compressed. In the middle frame, the ball had sped up, and become greatly compressed. So it's speeding up as it goes, but the compression was at its maximum. So then in the third frame, the ball is moving very fast and is no longer really maximum compressed anymore. It's almost not even compressed at all. So that's kind of these 3 points here. The contact began, the point of maximum compression here, and then the contact ends. So note that there's a well-defined duration delta t. So that was from here to here of the force. The large force like this applied over the short interval is our impulsive force. So other impulsive force examples, the hammer on the nail, and that force drives the nail into the wall. So as the hammer is making contact, it's going to create some sort of graph that looks like this. The baseball bat on a baseball, again, we'll see some sort of graph like this. We're going to have a contact begins, a maximum compression, and then sort of a contact ends, but there will be a duration delta t. It's basically the same graph, same idea. Golf club hitting a golf ball, same idea, okay? The harder kick, so that will give us, the harder the kick on the soccer ball would give us a taller force curve up here. The kick of longer duration, so maybe the ball was a little bit flatter, less air in the ball, would give us a wider curve. So maybe it would start over here and end over here or something, okay? The kick of longer duration, wider force curve, will result in the ball leaving the foot with a higher speed, maybe, or if it was a flatter ball, maybe a less speed, just longer duration because it didn't receive as much a force up top. So resulting in the ball leaving the foot with a higher speed, the effect of the kick is larger. So if we didn't flatten the ball, we just have a wider curve. That means that we kick the ball with a harder force, which means it's going to maybe we kick the ball with a longer duration. So our foot was contacting the ball longer is what I mean to say. Then we're going to be able to kick the ball farther. If we kick the ball with a harder force, so that puts us up here, we're going to be able to kick the ball farther, okay? So longer duration or bigger force kicks the ball farther. All right, so the taller or wider force versus time curve has a larger area. So the larger area between the curve and the axis. So the area under the curve is what we're talking about now. The area under the curve is larger. If we make the area under the curve larger, we can change the effect of the impulsive force. And when we do that, then we are making the resulting, whatever it is, greater. Okay? The resulting impact, the resulting flight of the ball, greater. Therefore, we can say the effect of an impulsive force is proportional to the area under the curve. So the area under the force versus time curve is what we're looking at here. So the area under the curve is the impulse. So we have a new definition here. The area under the curve is the impulse, and the letter that we're using is J of the force. So impulsive forces. If we look at the graph here, the impulse J is the area under the force curve. So that's our new concept. The area under both force curves is the same. So what we're going to do is we're going to try to define. So we have this complicated looking curve here, the bell-shaped curve that we're looking at on top. That's a complicated looking curve. So what we're going to do is we're going to try to define a new curve that is sort of like the average of this curve up here. If we can create some sort of average of the upper curve, that will create more of a rectangle. And that's what we're looking at down on the lower curve. Once we do that, then we have a more simplified version of this complicated guy up here, and we can easily calculate the impulse J. So that's what this is talking about. This one down here has the same effect as this one up here. So the area under the rectangle is F average times delta T, has the width delta T multiplied by its height, F average. So if we find the average force, then we're going to be able to use this guy instead of this guy. So impulsive forces are complex, and the shape of the curve can be as well. That's why we try to find F average. and use the same duration delta t, and that gives us the same area under the curve as the real area under the curve. So the impulse J is F average delta t. That's the formula that we want to use. The impulse is newtons times seconds. Newtons are kilograms meters per second squared. So if we multiply by seconds, that'll get rid of the seconds squared part and just leave us with per seconds at the bottom. But we usually like to write, so instead of Newton seconds, we usually like to write this guy here, kilograms meters per second. And if you think about that, it's just mass times meters per second. So impulse is also a signed quantity. So it's a vector pointing in the direction of the average force vector. So which way is the impulse going? Up, down, left, right, whatever. It is a vector. Okay. So the figure shows smooth force versus time data for the bounce of a rubber ball. So what is the impulse on the ball and what is the average force on the ball?
The impulse is wait, is that T?
We have T on the horizontal axis and F on the vertical
What
axis.
is milliseconds?
So first of all, for A, the impulse on the ball,
It's the area, right?
J is the letter that we'll use. And notice it said smoothed force versus time. So it wouldn't look like a line segment up and it wouldn't look like a line segment down. They smoothed it for us, so it looks a little bit easier to work with. J is going to be the area under the curve. And how would I calculate that area under the curve easily? Yeah, it's a triangle. So we just do 1/2 times the base times the height. So 1/2 times the base, which is 8 milliseconds. So
are we going to change that to seconds?
You would turn that into seconds because the units of impulse are kilograms times meters per second.
So it's going to be 0.08 or 0.08.
Milliseconds, the prefix milli moves the decimal 3 places. So 0.08 seconds times 300 newtons. Okay? What is this then?
What's 8 times 4?
12 or 20?
It's point 1.2.
0.12.
It's 1.2.
It's actually 1.2. What?
Kilograms meters per second.
Kilograms meters per second. Good. Okay, now B. What is the average force on the ball? So we remember that formula that we just saw.
J is equal to
Impulse equals F average. So the average force times delta T. Well, we just calculated the impulse and they're looking for average force. So we would solve for average force, divide both sides by delta T. So we have average force equals impulse divided by delta T. So that's going to be 1.2 kilograms meters per second divided by delta T, which is that. What do we get?
150.
150 what?
So this is going to be kilogram times meters, right? Because the seconds get
Newton.
This is newtons. It's an average force. Yeah.
Oh, that's right.
Don't overthink it. Okay, so pretty straightforward stuff. Does it make sense that the average force is 150 when the maximum force was 300? In this situation, yeah, kind of. Okay. And then one more thing. The two graphs show smooth force versus time data for two collisions. Which force delivers the greater impulse? Any ideas?
C.
C,
Why is it C?
because on the first one, Yeah. 5 meters or 5 milliseconds to 300 newtons, and the other one's 10 milliseconds to 150.
Yeah,
Yeah, proportional.
yeah.
The same.
That's the area under the curve is the impulse. So we would do the area width times height, right? That is, even though we didn't change the units, 300 newtons times 5 milliseconds would be 1500 newtons milliseconds. And this would be 150 times 10 milliseconds, which is 1500 newtons milliseconds. They're both the same thing. So it's C. Good job.